Our speaker today is Abbadini from the University of Birmingham. He's going to tell us about quantifier-free fragments and quantifier-relation depth in doctrines. Please.
Thank you very much, Luca. And I'm very happy to be here talking. And thank you all for being here. This talk is going to be about algebraic logic for first order logic. And algebraic logic has a certain feature that it forgets a certain syntactic information. So, for example, if you have a classical propositional theory, T, then you look at the Boolean algebra of all propositional formulas, modulo interprobability, and then the structure of Boolean algebra forgets what are the pure propositional variables and what are instead just the other Boolean combinations of these propositional variables. And this is a nice feature of the algebraic approach to logic because it is presentation independent. Similarly, in the algebras of classical first order logic, that we'll see later, some syntactic information is lost. You cannot distinguish anymore what are the quantifier-free formulas and what, for example, is the quantifier alternation depth. And again, this is a beautiful feature of the algebraic approach, but maybe at certain points we want to track some of this syntactic information and combine algebraization with some of this syntactic information. So in order also to transpose certain problems, certain questions in logic, syntactically defined to this algebraic setting. And so in this talk, I will present one way in which we can talk about quantifier-free formulas, quantifier alternation depth in these in the algebras of classical first-order logic. The inspiration here comes from certain step-by-step methods in the propositional setting, and I have a couple of slides about this motivation. They will not be needed for the talk, but it's useful to get an idea of what kind of things we would like to do. Okay, in propositional modal logic, an important algebra is the free modal algebra over a finite set of variables. This is what you get if you take all propositional modal formulas with variables from P1, Pn, and you mod them out by equivalence, by interprobability. And this is quite a complex thing already. When n equals 0, this algebra is already infinite because you can take 0, 1, H box, and diamonds, and it's infinite. But Guillardi gave a concrete description of such an algebra using step-by-step methods. So the idea is that you describe your algebra as a directed union of certain subalgebras over which you have control. And so it's an inductive procedure. You first describe the algebras of formulas with no modalities, and then you freely add one layer of modalities, and you show how to go from step 1 to step 2, and then you add new layers of modalities without destroying the previous modalities. And each step you can control, and at the colimit you get a union which over which you have some control. And he did something similar also for Heyting algebras, which are the algebras of intuitionistic propositional logic. And the idea is, again, to have some control over the free algebra. You stratify your formulas by implication depth, so by the difficult connectives. And he used this description to get some results. For example, that every Heyting algebra is a is a bi-Heiting algebra. Every freely generated Heiting algebra over a finite set is a bi-Heiting algebra. Okay, but what I just want you to retain from this slide is that stratifying formulas by the difficult connectives can give you some more control over the whole algebra. Also, another example of this stratification is in the following conjecture. Now, the algebras of intuitionistic propositional logic are Heiting algebras. The algebras of intuitionistic higher order logic are toposes. And there's this conjecture by Pitts that says every Heiting algebra is the algebra of subterminal objects of some topos. And roughly speaking, this means that if I have an algebra of an intuitionistic propositional theory, then this is also the propositional fragment of an algebra of some intuitionistic higher order theory. This is known for special cases. And Dito Badaraya announced a solution. Unfortunately, he passed away, so we don't have all the details of this announced solution. But the main idea for what who worked on this, who's looking at his note, told me is that he starts with a Heiting algebra and you extend it step by step until you get a topos, and in such a way that at each step you can control what are the subterminal objects of some topos. Okay, again, here there are some technicalities, but what I want you just to remember is that constructing algebra by adding one layer of the difficult connective, in this case quantifier, step by step, can give you something that over which you have control, that you can find properties about it. So here in this case, at the end you get a topos where you know that the subterminal objects form the original Heiting algebra. Okay, in this talk, I want to address the case of first order classical logic. Here, the difficult connectives are the quantifiers. So, we want to develop step-by-step methods for nested quantifiers in the algebras of first order classical logic. Here, what are these algebras? These are called first order Boolean doctrines. They are essentially to Louvier. We will recall what these are. And in order to recall this, I take a synthesis. For simplicity, in this talk, we consider only monosorted languages with only relational symbols and no equality predicates. Okay. So let's see what is an algebra of first order logic. If you have a first order theory, T, in first order logic, the idea to get an algebra is that for every context, for every set of possible free variables, you associate to it a Boolean algebra. Which Boolean algebra? The algebra of formulas with those variables as free variables. Modulo T interprovability. So, first component of the algebraic structure associated to a first order theory is an algebra for every tuple of different variables. And then, second component of the algebraic structure is something that connects all these Boolean algebras, which are substitutions. So if I have two different tuples of distinct variables, x1, xn, and y1, ym, and you have a function from the first set of variables to the second one, then you get also a substitution, where given a formula with three variables in x, you get a formula with three variables in y, where you replace each variable xi with the value that the substitution takes. So with a variable drawn from here. And this is, again, part of the algebraic structure of the algebra associated to first order theory. And then the last piece of structure is quantifiers. Here, if I have for all couples of distinct variables x and y, we have functions that take a formula alpha in context xy, so with three variables x and y, and you quantify over y, either universally or existentially. Right. So these three things are the constitute the algebraic structure. One algebra for every context, substitution that connect this context, and quantifiers. And if you want to axiomatize the structure that arises in this way, these are precisely first-order Boolean doctrines. And what are the axioms? This is the axiom. These are the axioms. The first-order Boolean doctrine is consists of the following data. For every tuple of distinct variables, x, you have a Boolean algebra. And the interpretation is that these are the algebras of formulas with free variable in x. For all, and then we have something that connects these different Boolean algebras. These are the substitution for all two tuples of distinct variables x and y, and every function from the set of variables x1, xn to y1 and yn. We have a Boolean homomorphisms. And all these Boolean homomorphisms satisfy functoriality. Namely, they behave well with respect to composition and identity. And then we also have these abstract functions that interpret universal quantifications. So for every two tuples of distinct variables x and y, you have a function for all y that takes an element of this set here to be thought as a formula in this context, xy, to an element in this Boolean algebra. And yeah, the existential can be defined from this, so we can avoid taking it as part of the signature. And these functions should satisfy the following properties. First, that quantifiers are adjoint to dummization. What does that mean? Now, here, if I take a for all statement, for all y, beta of xy, well, when is it above a certain formula alpha of x? This means, when can I prove for all y, b of xy, beta of xy from alpha x? Well, to prove a for all statement, what do? You discard, you remove the for all, and you think of y as a free variable. And so you prove that alpha x, where y is dummy, proves beta xy. So there's this equivalence. And then second condition is that substitution commutes with quantification. So if I have a for all y alpha xy statement, and I replace all variables x with by a substitution, then that's the same thing as before doing the quantification, replacing all variables xi with the variables given by the substitution, and then quantifying over y. There's a side condition that the variables here should not be captured here, but that's essentially the thing. Okay, and these are precisely the algebras of classical first-order logic. So, just like Boolean algebras are the algebras of classical propositional logic, first-order Boolean doctrines are the algebras of classical first-order logic, and they can be thought of as many sorted algebras. So one algebra for each possible tuple of variables, or certain functors. And the actual definition is a bit more general and captures also the case of many sorted languages, the presence of function symbols. Okay. But as I said at the beginning, the algebras lose some syntactic information. So, for example, we don't know anymore which formulas are quantifier-free. For example, take these two different theories. First example, take the theory of partial orders in this usual signature. Second example, second case, that take the theory of partial orders, but you add an additional unary relation symbol, minimum, together with the axioms that defines essentially minimum. That says, okay, for all x, min of x, if and only if for all y, x less greater than y. But this is saying, oh, yeah, I have one additional relation symbol in my signature, but then this is completely by the language without that symbol. And as a result, we get two different theories, but with isomorphic first order Boolean doctrine, with isomorphic algebra, but where in one case mean, in this case, second case mean is a quantifier-free formula, and in the first one it's not a quantifier-free formula because it's defined as for all y, x less or equal to y. So this notion of quantifier-free formula is not intrinsic in a first order Boolean doctrine. Yeah, and in this talk I want to give some more structure to these algebras so that we can talk about quantifier-free formulas. We can talk about quantifier detection depth and so on. Right, these are the main goals. Introducing enough structure to talk about this syntactic notion, and also give an explicit construction of free algebras, like it was done for modal algebras and heightened algebras. Okay, let's see quantifier-free formulas. Do you have any question up to now? Okay, quantifier-free formulas. Well, if you have a first order theory, we have this first order Boolean doctrine, the Lindenbaum-Tarski algebra, and inside it we have the algebra of equivalence classes of those quantifier-free formulas. What kind of structure does it have? Well, it's called a Boolean doctrine. Namely, a Boolean doctrine is essentially the same definition of a first order Boolean doctrine, but you don't have quantifiers. So you just have the Boolean structure, one Boolean algebra for every possible tuple of variables, and the substitutions. And so, okay, let me go back for a second. And so the first objective is to understand what is the abstract relation between this algebra of just quantifier-free formulas and all the algebra of all formulas. And this we capture in the following definition. So, quantifier-free fragment. Quantifier-free fragment of a first order Boolean doctrine is a Boolean subdoctrine P0 of P that generates P. What does it mean? Boolean subdoctrine means a many-sorted subset of P that is closed under Boolean combinations and substitutions. Right? Because quantifier-free formulas are closed under Boolean combinations and substitutions. And generating means that if you close also under quantifiers, here we have to take quantifiers, Boolean combinations, quantifier, and so on, then you get the whole P. And well, and that's the correct notion, meaning that if I have a quantifier-free fragment of a first-order Boolean doctrine P, then there is a theory T such that P is the Lindenbaum-Tarski algebra of T, so the algebra of all formulas for T, and P0, well, modulo T, and P0 consists precisely of the quantifier-free formulas. Or in the propositional setting, this is analogous to say, well, X is a generating subset of a Boolean algebra. Sorry, if X is a generating subset of a Boolean algebra B, then there is a propositional theory for which the Boolean algebra associated to it is up to isomorphism B, and X is precisely under this isomorphism the atomic propositional formulas. Okay, and now that we can talk about quantifier-free quantifier-free formulas, we can also introduce quantifier alternation depth. Now, okay, if we have a quantifier-free fragment, P0 and P, you should think of these as all formulas, just quantifier-free formulas. Then we can stratify formulas by quantifier alternation depth. P0, P1, P2. Where here quantifier alternation depth means the maximum depth of alternations of existential and quantifiers, or universal. And then we get a stratification of P. P is the union of all these many sorted subalgebras, P0, P1, P2, and so on. And since then we would like to construct P in a certain sense freely from P0, it's useful to have an axiomatization of these sequences that does not involve P, the ambient doctrine. And so what we next give is an intrinsic axiomatization of the sequences P0, P1, P2 of formulas stratified by quantifier alternation depth. That's the definition. We call it a QA stratified Boolean doctrine. This is a sequence of Boolean doctrines. So here we have substitutions and Boolean operations, but not quantifiers. This is nested, meaning that P0 embeds into P1, embeds meaning that it respects these operations, P1 embeds into P2. And moreover, we have this stratified universal, this stratified quantifiers, that in this case go from Pn of xy to the next layer, Pn plus 1 of x. And these should satisfy certain axioms. These are the following. Well, let me go back for a second. Here I'm asking that it goes to the next layer because by universally quantifying, I'm adding a next layer, another layer of quantifiers. And recall that Pn of xy are the formulas with quantifier alternation depth at most n, but here at most n plus 1. And and essentially these are the axioms. So again, we have quantifiers that are adjoint to atomization, but here we have to stratify it. If I have a formula for if I have a formula beta in Pn xy, I can look at its universal closure with respect to y, and I tell you what are the formula alpha x below it. These are precisely those such that alpha xy is below beta xy. And then we have this Beck-Chevalet, which means that again we have a commutation between quantifiers and substitution. And here we just need to consider, well, same thing. I'm quantifying and then substituting at level n plus 1. This is the same thing as substituting at level n and then quantifying. And then one last condition is that this plus Pn plus 1 contains just those formulas that arrive from Pn. So Pn plus 1 of x is generated by taking all formulas with quantified alternation depth less or equal than n, quantifying them, and then taking the Boolean combinations of these. Okay. And this is the correct notion, meaning that for any meaning that QA stratified Boolean doctrines capture precisely up to isomorphism the sequences of this type, LT0T, LT1T, that we obtain if we start with a first order theory and then we stratify all formulas by quantified alternation depth. Right. And now we've seen all the maximization of all the sequence. But if you want to build layer by layer, it's good to have a maximization of the finite sequences. And this we don't have yet. But the question is, for any n, which is the algebraic structure of the finite sequences of the form? You take formulas with quantifier alternation depth less or equal than 0, so quantifier-free formulas, up to formulas with quantifier alternation depth less or equal than n. And then you ask, what is the algebraic structure? What are the axioms that capture the structure arising this way? And we don't know yet. The conjecture is that you look in the definition of quantifier QA stratified Boolean doctrine, and then you just take those axioms that that make sense, that don't involve any k greater than n. Okay. But this is left for future work. Except the easiest case with n equals 0. For n equals 0, these are the Boolean doctrines. So, Boolean doctrines are, remember, Boolean doctrines are same thing as first order Boolean doctrines, but with no quantifiers. You just have substitutions and Boolean operations. And these are precisely the structures that appear in some QA stratified Boolean doctrine. It was said in a different way. These are precisely the structures that are quantifier-free fragment of some first order Boolean doctrine. Okay? And the difficult inclusion says that if I have a Boolean doctrine P, then there is a first order theory T such that P0 of x for any context x capture precisely the quantifier-free formulas modulo T with free variables x. And the idea for this is the following. P0, a first order Boolean Boolean doctrine, captures, encodes a universal theory. So a universal theory means that the axioms are all of the form for all x, alpha x, with x alpha quantifier-free. Essentially because in a certain sense you can remove for all and think of this as free variable. And this universal theory is the theory that we are talking about. And this is the free way in which to obtain a QA stratified Boolean doctrine. Okay, if you have any question, feel free to ask. Yes.
When you say free way, is there an injunction?
Excellent question. Good question. Indeed, there is. The forgetful functor from first order Boolean doctrines to Boolean doctrines over a small category So this forgetful functor that forgets quantifier has a left adjoint. Excellent question. Which freely adds quantifiers. One way to prove it is that first order Boolean doctrines are defined by quasi-equations. So, and quasi-varieties have free algebras, essentially. And we, given a Boolean doctrine P0, we call quantifier completion of P0. There's a first order Boolean doctrine P3 that we obtain by freely adding quantifiers. So P0, you should think of it as encoding a universal theory, and P3 as all the formulas modulo this universal theory. This comparison map is injective and generating. So P0 in fact is a quantifier-free fragment of P3. And then, okay, and now one of the aim that I said at the beginning was, given a Boolean doctrine P0, can I construct in a concrete way, in a manageable way, P3, the quantifier completion, where I add all quantifiers? Well, the fact is that it's a bit difficult to do it directly because here formulas have arbitrary complexity, like might have different nested quantifiers, quantifier alternation depth, so big as you want for all exists and so on. But we can make it more easy if we stratify this P3 and say, okay, I can stratify it by quantifier alternation depth, P0, then P1 free, P2 free, and so on, and get this as a colimit. And what we did, and what I'm going to present, is how to construct this P1 free over P0. And then the rest is for future work. Okay. And this is essentially, by this I mean, this construction of P1 free, which is the algebras of formulas of quantifier depth less or equal than 1, freely constructed over P0, the Boolean doctrine P0. This is a doctrinal version of Herman's theorem for formulas of quantifier alternation depth less or equal than 1. How much time I have left?
50 minutes?
Including questions?
No, like 12 excluding questions.
Okay, thanks. Okay, and let's recall that a simple version is the following. If you have a universal theory, or maybe you can think of the empty theory if you prefer, and alpha is quantifier-free, then the formula exists x alpha x is provable from T if and only if there are term definable constants C1 Ck such that you can prove alpha C1 or alpha Ck from T. The down to up direction is immediate, because if you have some constants, then you can prove that exists some x. And the interesting thing is that the converse direction also holds. And this is a way to reduce a formula, a probability of a formula with quantifiers to the propositional setting. And that's the kind of thing that we want for a free construction. Okay, it can be also formulated in more generality to characterize when two formulas of quantifier alternation depth entail each other. So, for example, here, if I want to know when a conjunction of a for all y, alpha y statement exists w without w entails for all z, gamma z, or exists v delta v. What do I do? Well, I can remove, so an existential hypothesis, you can remove it and think of w as a generic element, so a free variable, right? And also the for all, if you want to prove a for all, then I can remove the for all and just think of z as a free variable. And then if I want to use a for all as a premise, what I can do is I can instantiate it in infinitely many constants. And similarly, if I want to prove an existential, I can instantiate it in infinitely many constants. And in fact, Herbert's theorem says also that this formula here, the formula above with quantifiers, is equivalent to the existence of certain term-definable constants, such that this holds at the propositional level. Good? Any question about Herbert's theorem? And that's what we did at the doctrinal version, the doctrinal level. So we made a doctrinal version of this Herbert's theorem for formulas of quantifier alternation depth at most one. And the theorem is as follows. You have a Boolean doctrine over a small category. Then we have some statement that says how to transform inequality between formulas of quantifier alternation depth less or equal than 1. Since it's gray. Formulas of quantifier alternation depth less or equal than 1 in the quantifier completion of P0 into an equivalent existence of terms such that certain inequalities hold in P0. If you want the precise statement, it's this one. Maybe I will not go into much depth, but essentially here we have an equivalence between two things. One with quantifier-free formulas and a quantifier in front of it, an existential before a quantifier, and so on. And the second condition is a condition of existence of certain terms such that something holds at the propositional level. And this describes the order, and so the algebra P1-free of formulas with quantifier alternation depth of most one, freely constructed over P0. And again, the fact that is done in this doctrinal setting, in its full generality, tells us that it holds also for many sorts. When we have function symbols, it also holds the same with equality. And the next steps for future work are how to add further layers of quantifiers without destroying the quantifiers created at the previous steps. Okay, and this would give a step-by-step construction of the free first-order Boolean doctrine over a given Boolean doctrine. And in the end, it will amount to a doctrinal version of Herbert's theorem in its full generality. Actually, Herbert's theorem, I presented a simple version, the one which is usually presented, but Herbert had a way to reduce the probability of any first-order formula to the existence of certain terms such that something holds at the propositional level. And here, so if we do what we want to do, so give this step-by-step construction, of all quantifier completion. It will give a doctrinal version of Herbert's theorem, but probably we will not be able to mimic Herbert's proof, because the first thing that he does is to transform any first order formula in a Prenex normal form. And we're not sure whether this holds in doctrines for the following reason. Now, when you prove that every first order formula is equivalent to one in Prenex normal form, you use, for example, the fact that whenever you have a disjunction, you can put beta inside the existence, right? If you have exist x, alpha x, or beta, you use, in classical logic, in the usual approach, is equivalent to exist x, alpha x, or beta. But for first order Boolean doctrines, this doesn't hold in general. For example, when alpha is top and beta is top, this becomes top, and this becomes exist x, top of x. And in Boolean doctrine, first order Boolean doctrine, this is not true. Essentially because, okay, I've said to you that first order Boolean doctrines capture first order classical logic, but that's actually, there's a side note which is they capture the first order classical logic which is consistent with admitting the empty set. And if you admit the empty set, this is a quality is not true. So in this case, we will have to do, I don't know what, something else. But I think it's a good thing that we have a calculus where which is consistent with not admitting the empty set, because, for example, in our version of Herbert theorem, we didn't have any side condition. While if we go back to this theorem, here there's a side condition needed. If this is interpreted as usual classical entailment where we disallow the empty set, then if you take the formula exist x, r of x, or not r of x, these, if we discard the empty set, these would be provable. But if you don't have any constants in your language, then this is not true. And so you have to admit, you have to put a side condition saying that you have at least one constant. Yeah, in our theorem, in our doctrinal version, there's no such condition. But anyway, this is to say that I'm personally quite curious of what I will have afterwards. How this can be done without using Prenex normal forms. Okay, but just to conclude, the main goals were to introduce the doctrinal approach, enough structure, so that we can interpret quantifier-free formulas, quantify alternation depth, and also to get an explicit construction of free algebras. And these are our contributions at our future work. We axiomatize these quantifier-free fragments, so the algebras arise as so the inclusions of this type, LT0 inside LT, quantifier-free formulas inside all formulas. We axiomatized all the sequences, infinite sequences obtained from a theory T by stratifying by quantifier alternation depth. What it's left to do is axiomatize the finite sequences. But we did just the first case, which is n equals 0, which means that Boolean doctrines are precisely the structures occurring as layer 0. And these three are containing this preprint. And then we showed how to freely add the first layer of quantifier-free depth over a doctrine. This is a doctrinal version of Herbert's theorem for formulas of quantifier-free depth. That's regular one. And the future, we would like to do it for the next layers. So how to freely add the next layers without destroying the quantifiers that we have already introduced. Okay, that's all. Thanks.